audible from the back?
Yes.
Okay. So today I will be doing something which has not been done yet in TensorFlow user group Kolkata before. I will be speaking on machine learning for audio. As you, some of you might know, I am a machine learning engineer working primarily in the audio domain as well as in the natural language processing field. So, and also be aware this is possibly the fourth PowerPoint template possible. It was made overnight, and so here, next slide. So little introduction on me. Nothing much. I just do small little jobs here and there. Not really. I'm a Google summer of code contributor at TensorFlow. I'm a Kaggle master. I work as a machine learning engineer at Dynopii. I'm also a senior data scientist at companies called Predict and also Vocoders. So let's jump into the main. Okay, so as you might know, audio is basically a continuous signal, right? As I'm speaking, this is a continuous signal you are receiving. However, to convert it into a digital form, we need to sample those. But sampling, taking those continuous forms and then reading it in small interval of time, that's known as sampling. So this is a continuous signal wave you are seeing, and we take very small amount of time and maybe measure the amplitude over there. So this is a sample signal, and so in this image you are able to see those samples distinctly, but in normal audio it's not in a visible range where you can distinctly see. For example, CDs that play audio, they are sampled at around 44,100 hertz. Means in 1 second there will be 44,100 samples. Similarly, for high-res audio there is 192 kilohertz of sampling rate. In most machine learning models that we use, generally that generally operates on 16 kilohertz. But why the number 16 kilohertz? So happens there's a limit called Nyquist limit. So what's that? So it's basically the maximum frequency that can be distinctly heard is generally half of the sampling rate. Suppose I sample the audio at 16 kilohertz. So by Nyquist limit, the maximum frequency that can be heard is 8,000 kilohertz, right? And it happens that the human ears are able to hear at a maximum of 8,000 kilohertz. So what if we do this high-res audio? What if we use this high-res audio for training a ML model? Nothing much. We won't be able to make a difference. We won't be able to understand anything. It will just improve the computational load on the model, because basically 8,000 keywords we cannot hear, and by Nyquist limit half of 192 kilohertz is large. And also, what happens if we take maybe instead of 16 kilohertz we take maybe 12 kilohertz or 10 kilohertz? Then the maximum frequency that we can hear would be 5 kilohertz or 6 kilohertz, and with that the audio will sound muffled, right? So the next slide please. Yeah, the next factor for audio is amplitude and amplitude. Anyone with the physics in 11th or 12th might already know what's the amplitude, right? So amplitude is, sound is basically a change in the air pressure, and amplitude is how much, by what quantity that pressure, change in pressure is. So amplitude is generally measured in decibels, as you might know. And so the waveform that you see, louder. Okay, the waveform that you see, suppose this is the this and this the limits of those curves is basically the maximum amplitude that you are getting. And what's bit depth? Bit depth is basically the precision with which you can measure that amplitude. Suppose I take a bit depth of 16 bit. Ever heard this word 16-bit audio, 32-bit audio? So what does that do? So basically a 16-bit audio has a precision measure accuracy of maybe 65536. So there are 65536 steps while measuring the precision for a 16-bit audio. For 32-bit it is, for 24-bit it is much higher, and for 32-bit it is the same as 24-bit. However, in 32-bit the digits are in float. However, in 16 and 24-bit the digits are in integer. So yeah, that's it. Next. So how to represent a sound wave? A sound wave can be represented in several ways. The first of which is waveform. So a waveform is basically the change in amplitude with time. So as you can see, this is a 2.5 to 3 second audio. This is a 3 second audio of this audio is taken from the Librosa library. And as far as I remember, this is the sound of a night-angle bird, I guess. So this is a chirping of a night-angle bird, and this is a 3 second audio. This is how the amplitude changes over time. So this is a waveform view of your audio. Right. Next. We can also represent the audio as a frequency spectrum. Now, the frequency spectrum is not for the complete audio. It is for an instance of the audio, and here the frequency spectrum measures the different frequencies and the corresponding amplitude for that frequency. So suppose this the bird chirping, as you can imagine, the low frequencies will be higher. So this is a very low frequency, and as you can see, the amplitude is quite high for this frequency. So at a certain instance, what's the amplitude for all those frequencies is measured by the frequency spectrum. Okay. So, but what if we need to calculate it for the entire audio? Then we use something called a spectrogram. A spectrogram is the frequency spectrum, but just the frequency spectrum measured for the entire duration of the audio, means with respect to time, right? So this axis is those frequencies that you are seeing in this range, that is changed to this range now, and this is the time axis. Okay, and what with the amplitudes? This color intensity that you are seeing, those intensities are represented by these color changes. The amplitude, suppose this is a 20, this is in 0, this in the -8. Okay, one question you might have. As I said, the why is it ranging from 0 to -8? Amplitude is generally measured from 0 to something range, right? Maybe I'm hearing 60 decibel of noise. We don't, so as the decibel increases, it's louder the noise. But so the thing is, digital audio is, in continuous audio we measure amplitude from 0 to some range. However, in digital audio, 0 is the loudest noise that can be possible. 0 is the highest amplitude, and as you go lower, in negative, that's a lower amplitude. So as you can see, 0 is the maximum amplitude, so this region is very strong. So this frequency is present in so next. So happens that the human ears are not really designed to hear all those frequencies at equal precision. So the human ear perceives changes in low frequency much more prominently than it perceives changes in higher frequency. Suppose you say me something in your audible frequency. Someone says it in a different frequency. I can understand the difference between that two frequencies. However, when the frequency gets too high, suppose maybe birds chirping at a very high shrill frequency, we are not able to understand that change so much. So taking that human ear into consideration, another scale was developed called the Mel scale. So the Mel scale is logarithmic in nature. So taking the spectrogram and then converting it to the Mel scale gives us the Mel spectrogram. As you can see here, can we take the previous slide? See, and now the next. These same signals are just put upwards, and so that more importances can be given to the lower frequency ranges, right? Because changes in this region are much more prominent than changes in those regions. So this is a Mel spectrogram representation, and happens that most modern models that we use take these Mel spectrograms into consideration as input. Okay. So we come to the pre-processing part. So what are the pre-processing things that we need to first resample the audio? It is a requirement for any ML model that we operate in the same sample rate as the input with which the model was trained on. You cannot be giving a 32-bit audio while inferencing, or maybe different, and when the model was trained on maybe 16 kilohertz. So resampling the audio data, and that's the interesting thing. While resampling, okay, we come to that in the last slide. But that's an interesting thing. If I forget, make sure you make me remind. So next we filter the data set. We filter maybe any data that is over maybe 20 seconds or 30 seconds. Whisper does it for 30 seconds. We can use it for 20 seconds. By the way, Whisper is the state-of-the-art speech-to-text conversion model developed by OpenAI. It is completely open source. You can try it. Filtering the dataset and also convert audio to model's expected input. So Whisper requires Whisper or any such model requires the audio to be in certain format, right? So that pre-processing needs to be done. So for Whisper, suppose as I told, it pads or truncates to 30 seconds. If an audio is less than 30 seconds, then after the audio ends, zeros will be added. Zeros will be added to make it a 30-second audio, and if it's more than 30 seconds, then it will be truncated. One thing that Whisper is different in this respect is that most other audio models require another self-attention, another attention mask, so that where that audio is ending is also provided, so that it can be included in the self-attention here. However, Whisper does not need that additional attention. So yes, and also the last is audio to Mel spectrogram. Okay, can I come to the questions now? Or you can go ahead. You can ask me.
My question is basically, if you are talking about adding the what family is it just for the sake of batching or is there any other?
No, it is not just for the sake of batching. Basically, when the software for audio, then it's a requirement that we all those audio samples the same time. Otherwise, the model starts to produce dubious audio in that way. So, suppose the audio is larger than larger than 30 seconds. So outside that, if the audio is shorter than that, then since in language there is a stop token, but in audio there is no such stop token, and it starts producing single shots. So the next slide, please. Okay. So coming. Okay. Yeah, padding and truncating. So, as a waveform is maybe an array of single-dimensional array of amplitude. So, suppose the audio is ending at 25 seconds. So, for those 5 seconds, if for Whisper it is 30 seconds, for any other model it can be different. If the audio is ending earlier, we add zeros to make it 30 seconds. If it is larger than 30 seconds, then we remove those things and make it 30 seconds. So that is the and now for the model, we'll be jumping back to the very old transformers, but you all have heard of that a lot. So I'll invite any one of you can explain the transformer system in depth. One each TFUG short first. Explain the transformer architecture here. What it does.
So I give a personal shot here. This is what I understand out of the transformer model. So it is like any sequence to sequence model. It has both encoders and decoders for itself. In transformers, what we do, we send in the inputs with positional encoding, so that every point has its own reference. We then pass it through multi-rate attention. Now, what multi-rate attention does is it takes out attention for every single position, every single entity in every single position with respect to the entire context. That is what multi-rate attention gives us. We add a normalize, we add the actual input and also feed in the normalized output through multi-rate attention, and then pass it through a feed-forward and relay network and also add a normalize after that. That is one encoder block. We pass it through several encoder blocks, and then the final output of the encoder blocks is passed to a decoder block. Now, decoder block takes in the entire context of the input. It's not any transformed version of the input, but the context through different multi-rate attention. It's more of like attention of every single entity in a position passed to all the decoders. It's a stack set of decoders which is passed through, and then the decoder uses the same mechanism as of the encoder. It generates output based on the positions and their attention through multi-rate attention, more of like back propagation kind of thing. That's what I think. And it also uses the positional encoding to generate the same context but in a different maybe a language, maybe a different output. Maybe if we are using for language to language translation, we input one language to take out output in another language. That kind of
So makes sense? Okay, I'll also explain, but that was right. So in this city, TFUG Kolkata patient. So basically, this is the encoder block. This is the decoder block. We input something, maybe text, maybe waveform, maybe spectrogram. We get some hidden states out from the decoder. This cross attention, by using the cross attention, we provide it to the decoder. The decoder generates something, some different output, and So basically know the transformer architecture, but let's jump to the input. How we take audio input for the transformers, right? So there are models like Web2 or HUBird. They take raw audio as audio waveform as input to the transformer input, and also there are models like the Whisper. They take the MES spectrogram as input. So these inputs pass through a convolutional neural network. The layers in the convolutional neural network, what it does is subsamples those audio, subsamples it until those audios are of 20 milliseconds each, and then the final layer of that CNN, it gives a 512 dimensional vector for each of those 20 millisecond of audio, right? So, and then those vectors are passed to the transformer encoder. However, problem with this approach. As you can see, for 30 seconds of input, and sampled at 16,000 hertz, it would give around 4,80,000 sequence length. So that's a huge number, and it will require a lot of memory. So what Whisper does is it converts this 30 seconds of audio into a MES spectrogram. So the 30 seconds of audio is converted to this 3000 sequence length and 80 wavelengths. So in this way we can reduce the memory usage, and then in the same way pass it to the CNN and to the transformer input, right? Next. So now the output. For if you want text output, maybe the application is speech to text. So for text output, we from the transformer decoder, we simply pass the output from the transformer decoder to a language model head. The language model head may be just a single linear layer, and from that we just get the use the softmax to get the probabilities which suppose let's say I find the probability of each of the characters, and then the highest character probability is the character. From softmax we can just get the highest probability. So by character we can go on 20. So that's for the text output. What if we need audio output? So for audio output, we use something called as a postnet. It's some additional CNN as well as linear layers. From the transformer decoder, we pass that to the postnet, and it gives a clean spectrogram. And from that, we use something called as a vocoder to get back the audio output. But question, we generated those MES spectrograms, right? From the audio wave, we use something called as a fast Fourier transform. Not fast Fourier transform, it's actually TFT, but fast Fourier transform is the only feasible way to perform TFT in computers. So we use a fast Fourier transform, and hence this MES spectrograms are generated. So why can't we just inverse that? It means from waveform to this spectrogram is generated using STFT. So we can just use the inverse STFT. However, the thing is the output that these decoder models are producing, the models are producing are only MPG. However, for reconstructing the audio wave from the Mel spectrogram, we use the phase as well as the amplitude. So what this vocoder model does is it estimates the phase, because phase information is missing from the output that's produced by the decoder. So that's a function of the vocoder. So let's jump into some automatic speech recognition techniques. So there are two popular techniques, the CTC architecture as well as the Seq2Seq architecture. Right. So let's jump to the CTC architecture. Because the CTC is the simplest architecture. Okay, the CTC architecture stands for Connectionist Temporal Classification. So there are several models like the Web2, Newberg, MC. So what the CTC does? So basically, CTC is used for encoder-only transformer architecture. CTC is for encoder-only architectures where we pass a audio to the CNN, it goes to the encoder, and then it goes to a linear mapping. The hidden states that are produced by the audio, it goes to a linear mapping, and hence the output probabilities are predicted. But this is exactly similar to that of word. Can anyone say the difference? Can anyone say what's the difference? Because why do we need a CTC made in the first place? This is exactly similar to word. We are getting the sequence of hidden states. We are just using a linear mapping for that and getting the output probabilities. This is what word does. So for audio domain, one thing that's missing is the alignment. The alignment is missing for audio. In text, we know that this character comes after this, after and this after itna वक्त के बाद ये आता है. TEXT is not TEEXXXT. But for audio, that alignment is missing. We know which comes after which. For suppose the word error, ERR, we know the sequence. That is, it is a monotony. However, we don't know how many R's as such. So for that we use a CTC. Without a CTC, the output that's predicted would have been, suppose the example that I was giving. It would have been R, but that does not make sense while converting to text. So what the CTC it does is it introduces this small breaks, underscores you can consider small breaks, and that separates there are units of audio called phonemes. Phonemes are basically the smallest unit of what a sound can hear them. So the word error is broken into ER underscore RRR underscore OOO underscore RR. Suppose like this the word is broken, and we can then group those RRR OOO into one single R, one single O, and hence the word error is produced. So this is what the CTC layer does. Next. Now the sequence-to-sequence architecture. The sequence-to-sequence architecture is applicable for conditions where we use the decoder as well with the encoder. So this is the case for models like Whisper. We take the log Mel spectrogram, we pass it to the encoder, this is the cross attention, it goes to the decoder. What what can anyone at this point say me what's the in which purposes we use an encoder and which purposes we use a decoder? Anyone? When do you prefer using an encoder and when do you prefer using a decoder?
When we are taking an input, we are using an encoder.
When we are taking an audio input. But we can use encoder separately as well, decoder separately as well. But when to use which one? Okay.
Encoders for model input and decoder for.
No, encoder can also give output.
Secret transferring of data.
Okay. So the thing is, we use encoder for tasks like maybe classification, and we use the encoder decoder or just the decoder for tasks like maybe generation. So what this encoder thing is able to do is it is able to do one-on-one mapping, like for same for maybe say speech recognition. We take an audio and each of those phonemes are one-on-one mapped to a character, right? So for these purposes, for classification purposes, encoder is the choice to do. But if we want to generate things, if we want to generate text in a different language, maybe the GPT architecture that you see, generating text or unseen text, for those all are problems, the decoder part is able to generate unseen things, right? So yes, the difference in encoder decoder is that decoder has cross attention, so it's able to take the hidden states from the encoder and learn from it. It goes token by token, मतलब एक के बाद एक the start of SOT is the start of tokens. So it takes that, it produces an output. It again takes that sequence, produces a new output. Takes that sequence, produces a new output. Like that, it continues generating output until the end of text token is received. So, and also yes, the decoder is not able to see future information. So it's best suited for generating such stuff. It does not see future. Yes. Also, the last part, audio classification. We saw speech to text. Text to speech is also similar. We use those encoder decoder things. Just instead of using speech as input, we use text as input and get audio as output for those. So that's really similar. The next different application is audio classification. But audio classification is difficult. So how do we treat it? Just assume it is image classification. Yes, modern problems and modern solutions. So how, as I showed you previously, audio can be represented as images, right? In the mail spectrogram form, it is basically an image. So what we do is we just use a CNN like maybe ResNet, or even better if we use a vision transformer like and do something called as audio spectrogram, use something called as audio spectrogram transformer. So what this does is it takes those spectrograms, breaks it into 16 by 16 units, and then predicts an output for those, and after the end it just takes a sigmoid and then does the classification. So for the same in fact any encoder decoder that was trained for ASR can also be used for as a classifier. We just need to change the loss function. In case of ASR, it is the automatic speech recognition. It is the CTC loss, and if you want to make it used as a classifier, then it is just the cross entropy loss. Right. So yeah. And maybe Shamikda was saying this, but yes, there's a code as well where all those slides that you were seeing, those are all generated using Python codes. The code notebook will be shared, and as well now for the last part, I will be training a speech to text system that will be able to take Bengali speech and convert it to Bengali output, right? That's very rare these days, and even there's a Kaggle competition going on with that same task. I'll be doing that live. However, next slide. Before we jump into those codes, this is my contact information. You can scan it, or you can reach out to me in future if you need any help. Alright, do tag me in photos. The next slide. Okay, these are the two codes. This is the code for all the slides that you saw. All those slides are generated using this collab, and the collab that I am going to use now is this one. This is the code for the Bengali to Bengali speech recognition is task. We'll be applying all those things that we spoke previously into this one. So, okay, this code is taken primarily from the Whisper training that's by Sanchit Gandhi. He is from Amplitude. He trained it for some different languages. This is trained for Bengali. Also, the knowledge that I gave this talk is deeply inspired from his talks and his courses. So you can check him out. Also, I don't think we'll be able to run it now because as you can see this code we run it using a 300, and the dataset itself will take a lot of time to load. Bengali to data is more than 78 GB of it. So we can just scroll through this code. So first we install transformers and datasets. These are from Hugging. Then we do basically the notebook logging for publishing as well as downloading models from the hub. This is a common voice dataset. The common voice dataset is a collection of audios, and we download the Bengali version of those audio. As you can see, large data. We then filter out the dataset to use just the audio and sentence. We then get the pre-trained model, that is the Whisper small. We change the sampling rate of the audio. This this audio is in 48,000 hertz, as far as I remember. Audio is changed to 16 kilohertz because that's what Whisper requires. So after that, this is just the prepare dataset function for using all those preprocessings. We also pad our audio to 30 seconds as I mentioned because that's what is required by Whisper. So we pad those to 30 seconds. Yes, this is a data class. This is a data collector class that is from. And for evaluation, we will be using the word error rate metric. So word error rate is the number of words the model is able to predict correctly for some given text. So word error rate is the most commonly used metric for speech recognition systems. We do Whisper. This is the trainer, interface trainer. The interface trainer does most of the heavy lifting that we require for training our audios, and we call the sequence-to-sequence trainer. As you remember, Whisper is the sequence-to-sequence model. We call the sequence-to-sequence trainer, trainer.train, and here we can just publish the model and yes. Okay, so that was my presentation. In case of any query, you can just reach me out on Twitter or any other places. I share my contact already. So I don't know who does not yet arrive.